I wanted to provide a brief summary of how we use pumping test data in order to estimate aquifer parameters at depth. We previously discussed the partial differential equation associated with transient flow, and you'll recall that we had both storativity and transmissivity as constants or parameters of our differential equation, and it is in fact the solution to this differential equation that we're going to be using in order to estimate those parameters, transmissivity and storativity. And the actual solution of the differential equation is terribly complex, and we're never going to actually use it in equation form. We're only going to use it in a graphical form. In fact, you can make your own graph of u versus wu. It's called the well function term, using the data in table 6.5.1. And you would need a separate drawdown, so you would need a different solution and different curve for unconfined aquifers. And we're going to only use the graphical solutions for this differential equation. So don't be alarmed or concerned that it actually involves the solution of a differential equation. A number of different methods of estimating aquifer properties or aquifer parameters in the field or in situ. The three different methods are available using pumping tests. We'll focus on two of those. The first is the curve matching approach, which your text calls a graphical solution. And I don't like that name because the second method is also graphical. So I'm going to call it the curve matching method or the type curve method. And the next method is called the Cooper-Jacob method. The curve matching method involves plotting drawdown versus time on a log-log scale. And the Cooper-Jacob method involves plotting drawdown versus the time on a semi-log piece of paper. And I'm going to go through how to use both of those methods here in this PowerPoint presentation. The book also mentions that we sometimes use what's called a distance drawdown analysis, but there we need to have a number of different borings in place in order to make observations about drawdown at different locations away from our pumping test. And the extra cost associated with drilling many borings is usually prohibitive, and we don't use the distance drawdown method very often. We sometimes use out in the field what's called a slug test, which is an observation made in a single boring, so that we just make one boring and we either withdraw or add a certain height of water to the boring and watch how the water level returns to its original value over time. And then we use that to try and estimate properties of the slug test. But the analysis of the slug test is actually very complicated unless you know a lot about the conditions of your aquifer in advance. So I'm not going to cover the slug test in our review of Chapter 6. The method we're going through involves the type curve matching method. Here you should use the plot, and here I've shown it in a very small form, that I distributed on the afternoon of March 7th. And I need you to use that one because the one I distributed last week doesn't match the scale of the log-log paper that I distributed at that time. So I tried again on March 7th, and please print out that attachment and use that in your work. In order to use the type curve matching method, we need to know whether we have confined or unconfined conditions. We need to know whether we might happen to have a leaky confining layer, whether or not we have uniform thickness to our aquifer, and a number of other parameters. Because for every set of conditions, we have a particular type curve. The only one I provided you assumes a uniform set of conditions, a uniform thickness for a confined layer with no leaking in the confining layer. So we'll only consider cases of that type. And there we'll have our plot of the well function, it's WU versus 1 over U. And we're going to be using this plot along with observations of drawdown versus time in order to estimate aquifer parameters. To do this, we need to plot our pump test data on log-log paper that's of the same scale as our well function curve shown here. Then we'll slide the two different pieces of paper across one another until we find the point at which our data falls directly over the type curve that's shown on this slide. Remember, I mentioned in class that the sliding we do has to keep the axes parallel. So when you're sliding the paper, you can slide up and down, you can slide left and right, but you can't rotate one piece of paper over the other. Once you find a good place where the data overlies the type curve, you can pick any point on both curves and call that the match point. And we'll be making observations of the WU, the U, the S, and the T associated with that match. Let me illustrate. On the bottom right of the slide, you'll see that we also need the radial distance from the pumping well to the observation well, where we're making our observations of drawdown. Now let's take a look at another way of seeing this. Matching process. So we have on two different pieces of paper. One involves the WU versus 1 over U, and the other one we have log of drawdown, or just drawdown. We never actually have to take the log of anything since we're plotting on log-log paper. So you plot the drawdown versus time on the log-log paper, and then you take those observations and you take that type curve and you slide them one across the other until the data happens to fall directly on the type curve. Once you do that, you can pick any point. It does not have to be an observation point. It does not have to be on the curve that the two fall in. It's just any point that is common to both scales, and we will get four data values. One is WU and U from one piece of paper, and the other is drawdown S and T, time, on the other piece of paper. Once you have the S, the T, the WU, and U, or 1 over U, then we can calculate the transmissivity and storativity using these equations. And their transmissivity is equal to 114.6 times Q over the drawdown of the match point times WU of the match point. Once we have transmissivity calculated, then we can calculate storativity using S is equal to transmissivity times T from our match point, U from our match point, over 2693 times R squared in the denominator. I wanted to be sure to note that you have to be careful with units. In the example that I'm going to discuss shortly, your book wasn't careful, and I think they made mistakes, just being sloppy. Make sure you use a consistent set of units. If you're going to have Q in gallons, that's going to make it confusing. So you'll probably want to convert to cubic feet per minute or cubic feet per second in your Q, and make sure that your units match whatever you're using for drawdown and time. You'll see this in the example that follows. The method that we have of estimating aquifer parameters is the Cooper-Jacob method. And in this one, we plot drawdown on the non-log scale, and we plot the time on the log scale. And what we find is that the later time observations tend to fall directly on a line. If we draw that line and extend it on our graph to the point where it intercepts the time scale, then we can make this observation T0. We also need the slope of this line, which we represent by delta S. And delta S here is the change in drawdown associated with one cycle of time. So usually we pick T1, T2, we always pick T1 and T2 that are exactly one cycle away from one another, and we see what is the delta S associated with that. And with those 2 points, T0 and delta S, we're able to get transmissivity and storativity for this case, where transmissivity is 264 times Q, the pumping rate, divided by the delta S associated with one cycle in time. And now that we have transmissivity, we can then calculate storativity as transmissivity times T0, the intercept on the time axis, divided by 4790 times the R squared, where again, R is the distance from the pumping well to the observation well. Next, let's take a look at an example problem where both of these methods are put into use. So I'm going to ask you to consider the data from example 6.5.3, and I'd like you to look at both the type curve method and the Cooper-Jacob method and calculate the aquifer parameters for this confined case. So we want the transmissivity and the storativity for the aquifer in this confined case. The actual example in the book doesn't do both methods, and they lead to a different answer than I get because they're sloppy on units. But I use both methods, and you'll see that we get very similar results with, or fairly similar results with both. Let's run through what that looks like. Type curve method, again, we have to have the drawdown versus time plotted on this log paper, and that has to be on the same scale as the matching curve, as the type curve. And once we have those drawn, then you slide the two papers across one another and find a match point. The other method involved is the Cooper-Jacob method, and here we plotted drawdown, which is not on a log scale. So drawdown in feet here, and time in minutes, and notice that the time is on a log scale. So I plotted all the data, and I see that the later time data does fall essentially on a line, and I extend that line back to the intercept, and you'll see that our T0 is around 3 minutes, and our delta S we get from one cycle in time. So I went from time of 10 minutes to 100 minutes, and I used the line to estimate what our delta, the difference in drawdown is for one cycle in time, and I got around 2.04, and my units of drawdown are feet. So 2.04 feet is my delta S, and T0 is 3 minutes, and with that I'm ready to apply the Cooper-Jacob method. So I have associated PDF files where you'll see that I've actually shown you my plots and my hand calculations of transmissivity and storativity. The curve matching method gave us a transmissivity of 6,661 feet squared per minute and a storativity of 0.00013. And the Cooper-Jacob method gave us a higher transmissivity of 8650 feet squared per minute and storativity of 0.00035. In fact, the thing that's surprising here is how close the storativity values are. The transmissivity values might not seem like a very good match, but they actually are. It's very difficult to estimate these properties in the field. So when we report an average, I'll just use the average of the two methods and report a transmissivity of 7,700 feet squared per minute and a storativity of 0.00013. Notice that in my averaging, I only reported 2 digits because I think reporting anything more than 2 digits is just being giving a false sense of how precise our values are. Be sure to see the accompanying PDF files that go with this example discussion.